Welcome back, Digital Electronics. Moving on here, we're going to be going over binary adders. So we'll be using the XOR and the XNOR gates in some sort of combination to create a half adder and a full adder, which produces an adder for us. Okay, so we're going to talk about an XOR gate, an exclusive OR, an XNOR, exclusive NOR. And then we're going to go over how those gates can be implemented in order for us to make half adders and full adders. Okay, this is the XOR gate, exclusively ORed. So notice that it's very similar to the way the OR gate looks. Okay, except for it's got a little extra kind of line on the left-hand side that goes behind it. So what you really need to pay attention to here is the truth table to understand an exclusive OR. The difference between the OR and the exclusive OR is, remember, an OR gate, just as long as we had a 1 on somewhere on the truth table, our output would be a 1. With the exclusive OR, we are looking where the 1 is exclusively an X or exclusively a Y. But if it's X and Y is a 1, then our output's a 0. So we're looking for when one of the variables is a 1, not when both are. Okay, so if X is just a 1, we get a 1. If Y is just a 1, we get a 1. But if X and Y are 1s, we get a 0. So that's our exclusive OR, and there's how we write our logic expression. We have Z equals X bar Y or X Y bar. And another way of writing it that you might see on like the Siemens test is an X with a circle, an X with a plus sign and a circle around it, or Y. So that stands for X exclusively ORed with Y. Okay, so it is important that we understand the Boolean piece of this and what the logic gate looks like. This is the XNOR gate. So we're taking the exclusive OR gate and putting a bubble on the front end to invert the signal at the end. Okay, so what's really going to happen with the exclusive NOR, okay, is when we are looking for when it is not a 1. When either variable is not a 1. So if we look at the case of 0, 1 or 1, 0, our output in the truth table will be a 0. So another way of thinking this with the exclusive NOR is we are looking for when both of the variables are the same. So if both inputs are 0s, our output's a 1. If both inputs are high or a 1, our output's a 1. So that's another way of looking at that expression. And so notice that produces an X bar, Y bar, or a X, Y. And we can write that as X exclusively ORed Y with a not over it to produce the XNOR. Okay, so we're going to use the XOR here and the XNOR gate to create our half adders, and how we actually add and we can kind of subtract using our binary numbers as well. We're going to learn the techniques of how to subtract a little later on using a 1's complement and 2's complement method. Alright, but for now we're going to learn how to add using an XOR and an XNOR combination to produce a half adder and a full adder. Alright, so let's take a look at this. So if we have a logic design, alright, where we're using XORs and XNORs, so we can manipulate this expression here. So this is a bunch of min terms that we can manipulate down algebraically so that we can use an XOR or an XNOR gate when we do this. Alright, so we can use some Boolean algebra, things like that, to really simple down. So if we take that expression and we factor a Z out of the first part, we get we get Z times X and Y bar, or X bar and Y. Well, we know now automatically that that's a exclusive OR. So that's our XOR. If we factor a Y bar out of the second two terms, we're left with X bar, Z bar, or XZ. That's an exclusive NOR. So what we can really do is rewrite that expression as Z times X exclusively ORed with Y, or Y bar exclusively NORed with X and Z. So when we look at this, All right, it simplifies that circuit down, because notice before we would have had, a bunch of multiple OR gates there, 2 input OR gates, and a bunch of AND gates because we're only using 2 input AND gates. So we can see now how this translates down. So if we look at F1, we take that exclusive OR with X and Y. The output of that goes into an AND gate with a Z, all right, and that gives us our Z exclusive and ANDed with exclusively with our XOR. Okay, and then if we look at the next piece, all right, we got Y bar going into an AND gate, and then going into the other part of the AND gate is X exclusively NORed with Z. All right, and the outputs of those AND gates are ORed together then. So it really helps us get kind of a simplified scenario down here when we do this. All right, let's learn how to do some binary addition first, and then we're going to learn what a half adder does and how it handles things. Then we're going to put it into a full-on adder. So very, very simple. It's very close to how we traditionally add numbers, only when we do our carry, it's a little bit different as when we add. But 0 or 0. No, so I'm going to say or. I'm not going to say 0 plus 0 or 0 plus 1. 0 or 1 is 0, right? Or I can say 0 plus 0 is 0. But I still want to refer that to like an OR because we're talking logic gates on that, and we're using logic gates to do the mathematical operation. But if we have 0 plus 1, okay, that gives us a 1. If we have 1 plus 0, that gives us a 1. If we have 1 plus 1, that gives us a 0 with a 1 carry, and we bring that carry down. So 1, it gives us a 1, 0. But if we notice 1 plus 1 is 2, right? Well, 2 in binary is 1, 0. So everything still works out nicely here. All right, so every time we add 1, we're going to have a carry bit, or a 1 with a 1. We will always have a carry bit. Okay, even if we have a 1, 1, and a 1 that we add together, we will have a carry bit. Okay, so any other time when we have a 1 and it's not just 0 and 1 or 1 and 0, we'll be carrying. Okay, so let's take a look at multiple bit addition here. If we're going to add 0, 1, 1, 0 plus 0, 1, 0, 1, 1, okay, we're adding 6 plus 3 in decimal. All right, but for us, we're still going to work right to left just like old school math. So 0 plus 1 is 1. 1 plus 1 is 2, but we write 2 in the form of 1, 0. But 1 plus 1 is 0, right? And we carry a 1. And then we now have a 1 plus 1, which is a 0. And then we carry a 1, and we have 1 plus 0, which gives us a 1. Okay, so just make sure that you're understanding how that carry bit rolls. If we have 1 plus 1, we get a 0 with a 1 carry. If we have 1 plus 1, we get a 1 with a 1 carry, because 1 plus 1 is 3, and 3 is 1, 1. All right, so make sure that we understand how to do our binary addition and our carrying bits as we do this. Okay, so if we break this down, we have 1 plus 0, right? But then we have that carry in, which is a 1. So now we have 1 plus 1 gives us 2, right? 2 is in the form of 1, 0, but 1 plus 1 is 0. That's our sum, and then our output carry is that 1. All right, so we're going to use those here with adders. There's 2 types of adders. Okay, there's a half adder that has 2 inputs and 2 outputs, which are the sum and the carry bit. We use the half adders for the LSB, or the least significant bits, because those are the bits that constantly change as we cycle through a truth table. Then to get bigger and better, we use a full adder. So that handles all the other bits. Alright, so the full adder, we got 3 inputs. We have A, B, our carry in, so that's what the C stands for. C is carry, so on the left hand side when we're doing the half adder, C out is carry out. C in is the carry bit in. Okay, so when we have a half adder, we're only bringing in our 2 inputs, and then we're sending out what the sum is, and then the carry bit that goes out. When we have a full adder, okay, we're going to have A and B, our normal 2 inputs. We're going to have the carry in from the previous term. We're going to sum those, and then if we have a carry out or not when we go through this. So let's go ahead and take a look at how we're going to implement these. So understand the truth table of the half adder here. Notice how we have the two inputs, A and B, and we're going through our normal truth table of 0, 0, 0, 1, 1, 0, and 1, 1. Okay? So when we sum those, we know that the sum of A and B, okay, is going to fit into our sum column. We know 0 plus 0 is 0. We know that 0 plus 1 is 1. We know that 1 plus 0 is 1. And then we know that 1 plus 1, the output sum is 0, okay? And then we have a carry out bit there. So notice none of the others had a carry out. They were 0, 0, 0. And this is the only one that has a carry out. So that's how our half adder is going to work. This is going to handle, okay, all of the least significant bits that are going to constantly change back and forth. So we can see here the sum, okay, is going to have a specific circuit here. It's going to be A bar B, or A B bar, which is our A exclusively ORed with B. Our C out is only true when we have A B. So those are two important circuits that we're going to have to make and develop for the half adder. They're what's inside the actual half adder chip itself, but if we build and design the circuit on our own, those are the two important circuits that we need to make. The sum and the carry out. Okay, we're going to do the same thing when we do a full adder as well. But this is a half adder right here. So this is our half adder circuit. Okay, we have our A exclusively ORed with B, which carries the sum, and then we have our A and B, which is our carry bit. So that's what's producing the 1 when we have a carry. Now we're taking a look at the full adder. Okay, notice now the full adder has three inputs. It has A and B, and it has the carry in from the half adder. Alright, so that carry in goes in the place of the least significant bit. Okay, so notice it's the bit that's going 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1 as it goes through all of these. Okay, we're going to use those three inputs, A, B, and our carry in from our half adder to produce a new sum and a new carry out. So notice we're going to get a new sum and a new carry out, and we're going to write the equations for those. So our new sum happens when we have to add 0 plus 0 plus 0. Our sum is 0. We have 0 plus 0 plus 1. Our sum is 1. We have 0 plus 1 plus 0. Our sum is 1. We have 0 plus 1 plus 1. Our sum is 0 with a carry of 1. Okay, I'm just going right through the truth table here. Alright, and then we have the next one. We have 1, 0, 0. So 1 plus 0 is 1. Carry out is a 0. We have 1 plus 0 plus 1. Okay, that sum is 0. Our carry out is a 1. We have 1 plus 1 plus 0. Okay, that's a 0. And then our carry out is a 1. And then we have 1 plus 1 plus 1. That sum is a 1. And we also have a carry out of a 1. So we have different minterms. So for the sum, there is 1, 2, 3, 4 minterms that we're going to have to write, right? And for the carry bit, there's also 4 minterms. Now, we can do a K-mapping for it. So if we K-map C out, or that's the output for our full adder, all right, it simplifies down into A, B, or B carry in, or A carry in. Okay, so that's the simplification for our C out circuit. Okay, if we want to simplify the sum circuit, and we put all the ones in K-map, there is not a nice simplification for us for K-mapping. We can't group any ones together. They're all going to sit separately. We're all going to have those 3 input terms for the sum. So this part's for the full adder. Okay, so K-mapping doesn't help us here, so Boolean algebra is going to be our best bet here. So hopefully we can get down to some XORs or some XNORs. Remember, K-mapping helps most of the time, but isn't always effective. If we simplify down doing the Boolean algebra, I'm not going to go through all this because we've done this in previous lessons. At the very bottom, we notice that the sum output is down to literally just A exclusively ORed with B, exclusively ORed with C. Okay, so there's where that comes down to. So when we draw the circuit up for the full adder, this is it. Notice our three inputs, A, B, and carry in. The carry in is coming from the half adder. Okay, that's the carry out of the half adder. That's the carry in on the full adder circuit. Okay, so just make sure that you're paying attention to what carry in is coming from, okay, and what the carry out is going to. Because we can put multiple full adders next to each other to handle each bit. So the carry out of one adder is the carry in of another adder. We're going to cascade these together. Okay, so when we put them all together, okay, we're going to start making it look like this. Okay, this is if we just had AOI versus exclusive OR. Look how many more gates that was. So this is using just exclusive ORs. Okay, this is using AOI. A lot more gates involved here. So another advantage of using XORs and things like that and XNORs, we can compare and look at the number of gates and what it goes down to. That whole full adder, okay, this piece back here, I'm stepping back a couple slides. A exclusively ORed with B, exclusively ORed with C. Notice that's the circuit at the very bottom of this slide here. That's it. That's the full adder piece. Or it could be all those AND and OR gates and inverters at the top of the screen. So we can use one chip technically to make an adder. And instead of using, if we look at the logic above, well, we need an inverter, and then there's 8 AND gates, so we need 2 chips there, and there's 3 OR gates, that's another chip. So the circuit on top requires 4 gates, where the circuit on the bottom requires 1 chip. Okay, so 4 chips versus 1 chip. I think I said gate before, but I should have said chip. So there's 4 chips to make the top circuit that does the exact same thing as the bottom circuit does with 1 chip. Okay, so advantage of why we use XOR and XNORs when we do this. Okay, now this is our, remember MSI is medium scale integration, so this is our full adder. There's a chip for this, right? It's the 74LS183D. So make sure that you have that number written down for when we have to do some breadboarding or we do some interaction with some adders. Okay, 74LS183D, and you'll need to get the data sheet pulled up for that as well. So when and if we breadboard this one, all right, we'll have it with us. So if we look, we have our small scale integration full adder on the left hand side, which is equivalent to the chip on the right that does all the work for us. Okay, so what does that mean? A1, B1, those are inputs. The CN1, that's our carry in from the previous one. And then on the right hand side, S1 means sum out. And the 1CN1 is our carry out for this full adder as we go through it. Okay, so we're going to cascade adders, and you're going to do this in a lab and fill out a truth table, so you're going to be able to use the adder that you create to do this. Okay, so if we take a look here, we have the example we did earlier, which was 6 plus 3, right? We have 0, 1, 1, 0 plus 0, 0, 1, 1, and we know that it's 9, which is 1, 0, 0, 1. So this is kind of, taking a look at what we started off with in this lecture. Notice we're doing the same math here. We have A plus B, so A0 plus B0 gave us a sum 0, and then we had a carry out at the top. So if, when we have 0 plus 1 or 1 plus 1, that gave us a 0 and a carry out of 1. So the general form that we're looking at on here is really just how we would fill out, doing our normal mathematical operations like we did on the first couple slides when we first started to add these. Okay, so if we cascade this is to get a 4-bit adder. So this is something that you're going to be able to do in class. 4-bit adder means that we're going to be adding stuff that can go from 0, 0, 0, 0 up to 1, 1, 1, 1. All right, so just make sure that we're paying attention on this as we cascade them. Notice the LSB, the least significant bit, that's the half adder down at the bottom here. Notice that its output is going to be the inputs, the CNs for the full adders. Okay, it doesn't say C in on the left hand side for any of the adders, all right, because we're using the circuits. But that's where the value is that goes for the C in as you plug that in. Okay, because remember we have A, B, and a C in on each one of those full adders. So just make sure that you're paying attention how we cascade those when you do your assignment. All right, and don't get too worried about this one. The assignment's fairly well laid out for you as far as draw this circuit. It's going to be more you toggling through the switches and making sure that you're getting the values to come out correctly. All right, because this is another way to cascade it. This slide right here, okay, using the full adder, using the logic gates, is the exact same thing here as using the gates, only the specific chip here. So we have the 74 LS 183D. Now, notice what's the difference here on the full adder. We at the bottom when we had to do the LSB, notice that the input CN1 is going to ground. That's really the only difference here. That's how we make that full adder and turn it into a half adder. We take that CN and send it to ground. Okay, so this is what we'll do in class. We're going to cascade these so that we can add any numbers that are 4 bits, so 0, 0, 0, 0 up to 1, 1, 1, 1. Alright, we'll be doing this in class. And like I said, just like normal, email me if you guys at home have questions, or ask questions in class as we go through this assignment. Alright, take care guys, and we'll see you in class.